Welcome to study session 6. I believe you have really enjoyed the study session 5, where we discussed about elasticity and properties of matters. In this session, we'll be talking about hydrodynamics and hydrostatics. From the word hydro, I believe you should have the impression that we are going to be talking about fluids and liquids generally. After this session, I believe you will have been able to define and explain pressure, just like we briefly talked about pressure in study session 5. Also, you will be acquainted with the Pascal principle. Understand and explain Archimedes principle on your own. Then you will be familiar with the term hydrodynamics and be able to explain hydrodynamics. And finally, you should be able to state and explain Bernoulli's equation. I'm going to start with hydrostatics. Hydrostatics is about the pressure exerted by a fluid at rest. When the fluid is at rest, it's not flowing, it's stable, a stable fluid, and it's exerting a pressure or experiencing a pressure in its volume as a result of its position. Then we talk about the pressure exerted, in that case, as hydrostatics. Hydrostatics is about the pressure exerted by a fluid at rest, like I've said. Any fluid is meant, might not just be water, it could be kerosene, it could be petrol, it could be any available fluid. Since its outcome are extensively used in this study, the study will provide many suitable results or applications of hydrostatics. First of all, we will be looking at pressure. When a force F acts perpendicular to a surface of area A, the pressure P exerted on the surface is defined as the force per unit area. That is P equal to F over A. Pressure is a scalar quantity. Anyway, it has magnitude but no direction. The SI unit is Newton per meter squared. Now, I'm going to give you an illustration of what we refer to as pressure. Supposing a force is applied perpendicular to this surface area. Let's say this is the force applied to this surface area A. This area is said to experience a pressure given at P equal to F over A. The ratio of the perpendicular force applied across the surface is referred to as pressure. We have different measuring equipment that we can use to measure pressure. We call them gauge pressure or pressure gauge. Pressure can be measured using iron rod barometer. We can as well use manometer or boarding gauge. The boarding gauge finds its applications in measuring the pressure of a tire, like vehicle tire. Quickly, let's look at the characteristics of a fluid under pressure. The characteristics of a fluid under pressure is 1. Lack of rigidity exhibited by the fluid, and this has 3 major significant consequences. Number 1 consequence is this: the force a fluid at rest exerts on the walls of its container and vice versa always acts perpendicular to the wall. Take for instance, we have a fluid at rest. Inside this box, there's a fluid at rest. Now the force exerted by the fluid is always in perpendicular direction to the surface or to the wall of the container that contains the fluid. The force is always perpendicular. 2. An external pressure exerted on a fluid is transmitted uniformly throughout the volume of the fluid. Take for instance from the diagram, when you apply an external pressure on this fluid from outside, supposing you shrink the volume of the fluid, the pressure that is applied at this end is being transmitted uniformly to this end without being diminished. So the force applied at one end is being transmitted around the liquid body without being diminished. 3. The pressure on a small surface in a fluid is the same regardless of the orientation of the surface. The surface can be lateral, can be horizontal, but the pressure applied across that surface is always the same. When you apply a pressure, either small pressure to a fluid, the pressure is always the same around the fluid, irrespective of the orientation of the fluid. Quickly, let's look at pressure and depth. I'm going to illustrate that by drawing a simple diagram. Supposing we have a fluid inside this container. Now, imagine the depth of the container is represented as h. And we want to look at the relation between the pressure at every depth, either closer to the surface, pressure here, or pressure here. Now, the pressure inside the volume of a fluid depends on the depth below the surface. If a tank of height h and cross-sectional area A is filled with a fluid of density P, just like I've illustrated in the diagram, the volume of the tank is given as V equal to AH. That has to do with the area, the cross-sectional area of the tank times the depth or the height of the tank, the total height of the tank. And the mass of the fluid it contains is given mathematically as N equal to rho times V. That has to do with density times volume. Now, density given as rho is usually defined as mass per unit volume. So when we talk about the mass of the liquid, we talk about it with respect to the density and volume. Now, the mass can further be expressed as density times area times height, since volume equal to area times height. So instead of density times volume, can also be expressed as density times area times height. The weight of the fluid in the tank can be expressed as W, which represents weight, equal to mg, where m is the mass and g is acceleration due to gravity. Since m has been expressed as density times area times height, then the weight can be expressed as density times area times height and times g, where g is the acceleration due to gravity. The pressure in the fluid, represented as P fluid, is that on the bottom of the tank is given as P, as we know, equal to F over A. Then F is the same thing as weight. So P can be written as W over A. And since we have expression for W as P rho A H G, then the pressure can now be expressed as density times area times height times G over A. A cancels out. Then we have pressure at the bottom of the tank expressed as HPG. That is height times density times acceleration due to gravity. Meaning that pressure at the bottom of a liquid is independent of the cross-sectional area of the liquid. Rather, it depends on the height and the density, including the acceleration due to gravity, which is usually a constant, expressed as 9.8 meter per second squared. Now, let's look at Pascal principle. Pascal is a scientist that came up with the principle of relation of pressure with height of a liquid. Pascal principle states that any external pressure applied to an enclosed fluid is transmitted undiminished or evenly to every point in the fluid and to the wall of its container. I've illustrated that before. When you apply an external pressure to a fluid, the pressure goes around the entire body of the fluid without being diminished, and it touches every part of the fluid. Hydraulic press and lift are good practical application of this Pascal principle. In hydraulic press, the pressure on the piston is usually expressed mathematically as P equal to F over A. In recess, there are two pistons in hydraulic press. So we have P1 equal to F1 over A1 and P2 equal to F2 over A2, where A are the pressure, are the area of the pistons. So when a small input force is applied to the piston, then more load is being carried by the piston as a result of the uniform distribution of the pressure across the columns of the piston. Let's look at Archimedes' principle. An object immersed in a fluid appears to weigh less than it does outside the fluid. Take for instance, when you swim, your weight becomes suspended. You display equal volume of that fluid, which is equal to your original weight. So an object immersed in a fluid appears to weigh less than it does outside the fluid. The effect is known as buoyancy. Buoyance force equal to weight of display fluid is given as F equal to VPG from the previous derivation of weight as volume times density times acceleration due to gravity. V is the volume of the submerged object, which is also equal to the volume of the fluid display. The effects of buoyancy has diverse applications. It permits people to swim, ships to float, and hot air or helium-filled balloon to rise through the atmosphere. That is the principle which enables ship to be suspended on water and balloon to be suspended in air. Let's quickly look at flow rate and equation of continuity. The volume of liquid that flows through a pipe per unit time can be determined. I can express the volume of liquid that flows through a particular pipe. Take for instance, a water pipe per unit time. Mathematically as AVT. The volume can be expressed as AVT, where A is the cross-sectional area of the pipe. Therefore, the flow rate of the liquid through the pipe is expressed as R equal to AVT, that is the volume of the liquid that flows through the pipe per unit time, over T. And since we are talking about rates, we divide by T. So T cancels out. So the flow rate is given as AV, or if you have two pipes, A1B1 equal to A2B2. Now let's quickly look at hydrodynamics as we are through with hydrostatics. Hydrodynamics can be defined as a branch of physics that studies the behavior of liquids that are in motion. Don't forget, when we talk about hydrostatics, we talk about the pressure exerted by a fluid at rest. Statics, fluid that is in a position of rest. But dynamics has to do with fluid in motion. There are basically two types of fluid flow. One, laminar flow. Two, turbulent flow. In laminar or streamline flow, every particle of fluid passing a particular point follows the same path called a streamline. You follow the same path called a streamline. As the particle that passed the point earlier. So when there is a route for the particle, others follow. Also, the direction in which the individual fluid particles move is always the same as the direction in which the fluid as a whole moves. On the other hand, turbulent or irregular flow is characterized by presence of whales and edibles. Take for instance, a water that is flowing across stones of different particles trying to block its way. Such water experiences what we call turbulence. When a liquid flow through a pipe enters a region where the cross-sectional area is reduced, its speed increases, and that is what Ballooni's equation explains. When there is a reduction in the flow path or the cross-sectional area, then its speed increases. Take for instance a water tap. When you look at the pipe that runs from inside to the tap, is usually wider than the tap cross-sectional area. At the point of opening the tap, the water rushes out, the speed increases. The increase in speed was as a result of reduction in the pipe cross-surface area at the outlet. So a change in speed requires acceleration as well as a net force acting on the fluid. Let's look at the diagram we have on board. We have a larger section of the pipe. then we have a narrow section of the pipe. Now the flow rate in each section is expressed as V2 delta T. That is the formula. Then at the narrow section is expressed as V1 delta T, while the height of each section is given as H1, H2, and the cross-sectional area are expressed as A1, A2. Since it is fluid, we expect them to exert pressure along the columns and the velocity of the fluid to vary along the column. So those parameters has been expressed and put together to have what we call Bernoulli's equation. This equation gives a relation between the pressure in a moving liquid and its speed, and is given as P1 plus half rho V squared, which is the density, plus rho GH1, the height of the narrow side of the pipe, equal to P2 plus half rho V squared plus rho GH2. What this relation is telling us is that the total pressure in the column 1 with the density of the column 1 and the volume plus acceleration due to gravity and the height of the column 1 is equal to the total pressure in the column 2 plus density plus the volume and the acceleration due to gravity and the height of column 2. So this equation can be applied to solve diverse problems of liquid flows in different media. Thanks for listening.